Section 6.3, we're still calculating volumes. They're still volumes of revolution, but this time we have a little bit different method. This is called the shell method. Setup is very similar to before. We've got some region in the xy plane. For simplicity, we're saying it's a region that's bounded above by some curve y equals f of x, bounded below by some curve y equals g of x, and on the left and the right by values x equals a and x equals b, respectively. So what I'm going to do now, rather than rotating around the x-axis, I'm going to rotate this around the y-axis. Okay. Now I did an example before in a previous video where I rotated around the y-axis and I turned my rectangles to be sideways. This time I'm not going to do that. I'm sticking with my horizontal, what are these called? Vertical rectangles. So for every value of x between a and b, I have one of these rectangles. Generally, I just draw one, but you got to remember there's one here, there's one there, there's one there. For every value of x, you got one of these things. They're really skinny. They got a little width of dx, and the height is, well, the distance between the top and the bottom there. So when I rotate, just focus on one of them right here. Focus on this one. When I rotate around the y-axis, what's going to happen? That this rectangle is going to come up the screen, come off the screen at you. It's going to rotate all the way around over to this side over here. It's then going to continue back underneath the screen all the way back to here. And I'm trying to draw this in 3D, and it's always a little tricky. That rotates around, the outside rotates around, and the same thing back here. This would kind of be on the inside here. Each one of these rectangles would generate something like that. In fact, let me switch the camera and show you what I'm talking about. What I have here is one of my first attempts at 3D printing, something that I might use in one of my classes. So what it is supposed to be is there's a sine curve that just one bump of the sine curve that goes up and then back down again over here. Okay, and then I use the x-axis. So the top is the sine curve, the bottom is the x-axis, and then I rotated it around the axis that's coming straight up at you here. Rotate it around this axis. Each one of these things there was a rectangle over here that got rotated. So this is what I'm ending up with. I'm ending up with a bunch of these, what are called shells. They're not very thick because that's the dx. The height of them is the height between the sine curve and the x-axis, and then you rotated the whole thing around the y-axis. So each one of those little rectangles along the x-axis generated one of these shells. Now some of the shells have a bigger radius because they started off further away from the y-axis. Right? This is the outside one. It's got a really big radius. If I can get it picked up, there we go. All right, really big radius. But it's not very tall because the sine curve isn't very tall out there. Okay. Ones in the middle here, let's see if I can get these out, have a much smaller radius because they're not very far from the y-axis, and well, they're as tall as the sine curve is in there. Eventually the sine curve gets really pretty short in the middle here, so right in like that. So each one of those is a shell. Each one of those rectangles generates a shell, and what I'm going to do is I'm going to calculate the volume of this whole thing by figuring out the volume of each shell and adding them all up. Each shell will figure out the volume and then add them all up. All right, let's go back to working on paper. All right, so we need to calculate what the volume of one of these shells is. So what I'm going to do is I'm going to take that shell and I'm going to essentially slice it and open it up, unroll it. So it would be kind of a rectangle on the end, and then it would be really long, right, to a rectangle over there on the other end. It's a big long box. Now, as long as the thickness is very thin, as long as this is a very small thickness, then the distance around the outside is very close to the same as the distance around the inside, and I can just essentially ignore that difference. So now, if this is just a box, then the volume is going to be calculated by length times width times height. Well, the height is the height up here. Well, that's the distance between the top and the bottom. So there's a height of f of x. I'm going to need more room. So I'm going to write it down here. We got the volume is f of x minus g of x. The thickness is just a little dx. In fact, I'm going to write that over here. I'm going to write that last. And then there's the question of how long is this all the way here? Well, that length is the distance all the way around that circle. It's the circumference of a circle. Well, what's the circumference of a circle? Well, 2 pi times the radius. So 2 pi times the radius. Well, what's the radius in this case? The radius is the distance from the axis out to wherever your rectangle is. Well, the rectangle is at x, and I'm going to have one of these rectangles at a, and then a little bit more than a, and a little bit more than a, and a little. I'm going to have one for every single value of x between a and b. So the best way to describe that is that where is it? It's out here at x. This length is a horizontal length. You're going to be measuring. You're going to calculate it by saying what's the x value on the right side, what's the x value on the left side, and that will be your radius. Well, the x value on the right side is x. If I'm rotating around the y-axis, the x value on the left side is 0. So that x minus 0 is the radius of that shell. 2 pi times that is the distance. This length here is 2 pi times x. The height is f of x minus g of x. The thickness is dx, and the volume of that shell is all of this. Let's rewrite it in a slightly different way. Let's put the 2 pi x out in front. The f of x minus g of x times dx is the little bit of volume. Let's call that dv. To get the total volume, you need to add up the volume of each one of these shells. So the total volume, I think this is going to give me the total volume. Sometimes I don't know what this is doing. I tried to write a v, and then my computer's just kind of blinking at me. Here we go. The integral from a to b of 2 pi x times f of x minus g of x dx. Distance all the way around, 2 pi times the radius. The height of the rectangle, top minus bottom, times the thickness, and that thickness is a little bit of x. So dx. Let's do the example that I had in plastic there, my 3D printed one. Let's actually do the sine curve, the first bump of the sine curve. So I'm looking at this. I've got y equals sine x, just one bump of it. So from 0 to pi, this is y equals sine x. I'm going to rotate that around the y-axis. So it comes over here. This is rotated here. This is rotated on the back side. For each value of x between 0 and pi, I'm drawing a rectangle, vertical rectangle. That vertical rectangle gets rotated around the y-axis, and it generates a shell. Right? Actually, the 2 pi can come out in front. 2 pi times the integral from a to b. The radius is the x value right there, minus 0. The height function here, this is vertical, so it's the y value on the top, which is sine x, minus the y value on the bottom, which in this case is 0, times dx, thickness. So 2 pi, the integral from a to b of x, sine x dx. You could do that one by hand if you're feeling ambitious. It's an integration by parts. Oh, A to B, A to B. I know what A and B are in this problem, don't I? We're going from 0 to pi. So the integral from 0 to pi. And I'm going to do that on my calculator. I get 19.7392 and some change. One thing to make sure, if you're using your calculator on this, since you're using a trig function and you're doing some calculus with it, make sure your calculator is in radian mode. Derivatives and antiderivatives only work when you're in radian mode. So anyway, there is an example of the shell method.